Okay, I will continue. So all you have to do is to calculate this probability that we have right here. This one is what we need to do. So we have to calculate the probability that all zero code word was sent, and we have made a mistake with in favor of the second code word, or the third code word, or the fourth code word, or continue down on the list on the 16th code word. So since this is OR operations, so basically we need to add up all such probabilities, okay? And for each probability, there is a rate associated with it. So this is going to be the average error rate, okay? So we can continue, we can do the calculation one by one. So let's take a look at the second case, right? We made a mistake to the second code word. So when is the case that we make a mistake to the second code word? Basically, that is the case when received word belongs to the second code word. Okay, belongs to the second code word hemisphere, right? Or the second row. When the received word R is one of the element of the second row. So that is the case that we will make a decision based on the second code word in favor of the second code word. Okay, so the such a case occurs. So let's take a look at the second code word case. Let's go. Hold on a sec. Let's go to the second code word case. So second code word case, when we take a look, is we send this one, we made a mistake to this one, second code word case. That means the received word is one of these guys. One of these guys. Okay, and that means in this particular case, you made 4 errors, right? So 4 bits flipped, 3 bits flipped. So this is an independent IID channel. So all you have to do is keep track of these number of bit flips, right? So this is 3 bit flips. This is again 3. This is 5. 5 again. And 5 again. So there are 4 3-bit flip error events, single 4-bit error event, 3 5-bit error event. Okay. So 4 1 3. Okay. All right. So let's remember that. And probably I don't have to erase it right now. So just select mouse and go there. Right. Let's see. Right here. Okay. So 4 bit errors is represented right here. There's only one of them. Okay. 4 bit errors, only one of them, and then 4 3-bit errors is represented right right here. 4 3-bit errors, okay, and 3 5-bit errors, 3 5-bit flip errors, right? Single 4-bit flip errors, 4 3-bit flip errors, and then we add all these probabilities. That's the probability of this event. Okay, you send the first code word, and then you made a mistake in favor of second code word. And then we can continue to the next decoding error event. So for in this particular example, we have made a mistake in favor of third code word. And so we need to take a look at the 8 words in the second row, in the third row, and basically the weight counting that, as you have done right here, is 3 2 4 2 4 2 5 4. That means there are 3 2-bit flip errors and single 3-bit flip errors, and then 3 of them, 3 4-bit flip errors, and single 5-bit flip errors. Okay, so we have to add them up. That will be these the probability of this error event. We can continue on to the 16th code word. So we can repeat the same procedure. We can use the computer to do the repetition. Okay, thinking we need to do, and once we have figured out what to do, then we can ask the computer to do the program, to do the calculation. Okay, so we need to do a little bit of programming. So let me erase everything. So we can continue on to the 16th code word. So in order to calculate the information bit error rate, we need to complete a table of error rate in enumeration. So you sent a zero code word, or zero code word. That's the assumption. Then when j is equal to 2, 3, 4, 5, all the way up to 16, and the this is the weight info. In this particular case, this information bit weight is 1. Okay, and the number of patterns with the weight W. So weight 2, 0 occurrence, and weight 3, 4 occurrences, weight 4, 1 occurrence, weight 5, 3 of them. Okay, and this is 413 that we have before. Okay, 4 1 3 4 3-bit, 4-bit, 5-bit errors. So 3 4 5 4 1 3, and then for the third code word, starting from 2 3 1 3 1. Okay, starting from 2 3 1 3 1. I made a mistake. Need to so I made this mistake, so my result is going to be a little bit off, but since this is a small mistake, I don't think it will affect too much to the final answer. So when you download my computer code, I will show you soon. basically make this update and run the code. Okay, so I will write this as red letter. Okay, 3131. Okay, and then you can go on down to the end. I haven't. Yeah, go on down to the end. For all one code word, you have a weight 6 and 7, and such error patterns is 7 and 1 and so on. So we have complete the table, and then using the MATLAB file. So this was supposed to be 3131, huh? 3131. You use this array, and then you can do the calculation of a probability of bit error. And then you can draw the picture for different bit flip errors. So when you send raw messages, you will have to the channel introduces this much this much percentage of errors. So for example, the 10% error, 1% error, 1,000 error, and 10,000 error, right? You cannot do anything about this. But if you use a channel code, for the example of this one, you will improve it by this much. It's like this one is 0.5 times, so 0.05. So that is an improvement from 0.1, right? And if 1 over 100, this is like smaller than 1 over 1,000, right? And it was 1 over 1,000, then it is in the order of 10 to the minus 5. So you get a huge improvement. Okay, so that's the channel gain, right? Channel coding gain, right? So if you use the channel code, so then you can provide a protection against the random errors, and this is the how much you can protect. Okay, using length 7 channel code. And if we increase the block length to infinite, this channel coding benefit approaches the so-called channel coding limit. Okay, I mean the rate limit. Okay, it approaches the limit. That limit is nothing but the channel code rate. I mean that limit is nothing but the capacity of the channels. Okay. All right. So in this example, I have shown you how to calculate exact calculation, but exact calculation is very difficult to obtain, especially when you increase the length of the block code. So basically one point here is that it is very difficult in general to calculate the exact code rate. But even though we cannot obtain the exact error rate, there is a way to prove the channel coding theorem. Basically, we can use upper bounds and lower bounds. If probability of error is upper bounded, and this upper bound is approaching 0, then surely the exact error rate will approach 0. So we use such an argument to prove the channel coding theorem.